Yeah, sure.
All right, everyone, welcome to the last session of the day. It's wonderful to have Michael Douglas here. He's going to tell us about theorem proving AI in physics. Mike's at Harvard now, but he has had quite a career doing many different things. He's inspired those of us string theorists for decades, but now he's teaching us things about AI that we didn't know and theorem proving. So Mike, take it away.
Thanks, Jim. It's a pleasure to be here. So I'll talk about joint work, part of this with Sarah Hoback, a student here. And so there's this field of interactive theorem proving, part of formal methods of computer science, which is not AI. It was really started kind of along with AI and hasn't been AI for quite a while, or if it has, symbolic AI. But it's starting to really become quite important, and there are many people that think that this is, in a way, a missing ingredient in AI. And not only is it developing, it's something which I think physicists will really be able to use in the very near future. So I'll describe what is interactive theorem proving, and the lean theorem prover is probably certainly the most active one right now. An example of a physics project, and eventually a demonstration of how a coding assistant starts to make these things. It points the way. It shows that this is really starting to become something that one doesn't need to be a dedicated expert to use. Okay, so there's this very ancient question, what is truth, and what is mathematical truth and mathematical proof? And so people have thought about it forever. And around the year 1900, we'll say, it became realized that you could express a very substantial, and in fact, the core, the essence of mathematical truth and proof in terms of precise statements, mathematical logic, and not just precise, but something that you could really check an argument just by looking at the form of the argument. So a syllogism, according to Aristotle, is something where if you accept the premises, you must accept the conclusion because the argument has the right form. And then one could elaborate that into this whole system of mathematical logic. And of course, famously, there was this negative result early on that says that, well, no, provability is not the same as truth, and consistency is not something that we'll ever reach in this life. But for the broader question of, well, can you in fact use this to think about mathematics? Really, the answer is yes. You can formulate essentially not everything that we think about mathematics, but this concept of proof in precise formal terms. And so that is really also the origins of computer science. That just manipulating symbols in some way or electrons in a computer. You can do it without. You can ascribe meaning to the symbols, and they can satisfy properties that you would infer as a validity of an argument, for example, without having to somehow program in that meaning. You just have to follow the right rules. Okay, and so the basic example of that, which you've all seen, is propositional logic. And I'm just going to flash through a lot of these slides as familiar things, but to prime things that you've already seen. So we have rules of inference like modus ponens, and a proof would be a set of premises, a series of inferences using these rules. If you stick to those rules, a sound set of rules, then you know that the conclusion is proven. And the main point is that you can easily check that, yes, each rule was correctly applied. Now, it's in fact very hard to find in general, given a statement, is it true, is it not? Can you find the proof? That's the famous P equals NP. And in fact, it's different to exhibit a satisfying instance from proving that there's none. That's NP, not co-NP. And so it's this basic truth of computer science that verification is something that you can automate in a systematic and efficient way, whereas the actual process of finding a proof often involves search, and you have much less control over it. And so in the context of trying to prove things automatically, well, in general, it exists, but automatic proving is hard. But trying to check a proof and to help a, say, human mathematician make a proof, well, that's a a practical thing that you can automate. That's much like compiling or much like some other programming language problem that you might just solve. Okay, so I'm going to get to this. This is an example of this lean language. This is the proof that there are infinitely many primes, okay? And the statement up here is that for any, well, for any n natural number, there exists some greater than or equal to p, which is a prime, okay? And then that does imply the infinite number of primes if you think about it. And then I'll come back to something about this proof. I don't think I'll have time to spell it all out, but the basic message is that the computer can really check this and say, yeah, no doubt, there's an infinite number of primes. You proved it, and it's much more like a programming language than like traditional mathematical discourse. Okay, and as such, it's good to have some little, at least a little background in programming languages to work with it, to appreciate it. And so this is like computer science 0.01. The languages that one first learns, such as Python, say, are procedural, where you see a statement x equals x plus 1, and of course it's an equation. This is not very interesting. There's no solutions. But of course it's not an equation in a Python or in most programming languages. It's a statement that you're supposed to compute the right-hand side and assign it to the variable on the left-hand side, and thus change the state of the computer when you do that. And then that's very common in computer languages because that's the way computer hardware works. You stuff a new number into some memory cell, but it's rather far from the way that we think about mathematics. Usually we interpret this equation as an equation. And so there's this process of development that you might start with procedural language and throw away the things that are not like mathematics and add more things to make it more like mathematics. So that's one way of thinking about this. So functional programming is, for example, a paradigm where you combine and concatenate functions to accomplish operations. And that's a start. There's many more things, obviously, that you would need in mathematical argument. And again, I don't have time. I'm just trying to give you the sense of where these things come from and give you some references. Okay, so there's that aspect. There's sort of the engineering aspects. If you've done any programming, big programs, it's a lot of work just to keep track of everything, to keep track, to avoid using the same name twice in incompatible ways and so forth. And there's a lot of existing programming language technology which is useful there. Okay, so then what more do we need from math? Well, we need first order logic where you have variables, you have quantifiers such as for all x, there exists x, and so forth. This is pretty general, but not totally general. The big difference with higher order logic, which I'll get to in real math, is that you can't quantify over functions. You can only quantify over variables. So you're working very hard to rephrase things that are naturally expressed in terms of functions in that language. And for example, a real number, if you go back to the mathematical constructions, they basically require this ability to talk about infinite sequences, which are functions, and say for all infinite sequences, ... And so it's to express mathematics, you really need this high order logic. And then this is a lot of the interest from a logic point of view. How do you get this to work without coming into inconsistencies? But it's been studied for well over 100 years, and there are many, many very effective ideas here. So I'll mention that lean and really the most effective theorem provers use what's called a type theory. If you studied foundations of math, you know that it's usually based on set theory. And type theory is in some ways more intuitive, especially for a programmer, because you might make an analogy with types in a language like the integer, this variable's a double, this variable's a float, and so forth. And it is certainly a similar concept, but what's very essential and what's only partially developed in most languages is that you want a very general way of constructing types out of other types. So, for example, a matrix is not just a matrix. Well, there's, the entries have some type. They could be, some particular type of number with certain properties for the matrix operations to make sense, and then the two index sense. So you want the constructor of a type to be a function of these things. So there are these various properties which makes it convenient to express mathematics. And if you're missing them, it starts to become very difficult. So the current kind of state of the art, a lot of this was invented in this theorem prover called Coq over the years, but the current state of the art is something called a lean, in fact version 4. And so you can readily find things online about this. They have a very nice community website. They have a Zulip chat. This is a post with some explanations. This is able to express all of mathematics. There's a library which from some point of view is sizable. It's approaching 2 million lines of code. It has a lot of the undergraduate math curriculum. It does not have a lot of what you would need to express physics, unfortunately, but it's a good start. And so the projects that have been going on by mathematicians are things like the independence of the continuum hypothesis, this famous statement in logic. Kevin Buzzard's trying to verify the proof of Fermat's conjecture by Wiles, and so forth. So you can do hard things, but it takes a lot of effort. Okay, so to, again, give a flavor of this, these are examples of arguments. So how would you prove this statement, 2ab is less than or equal to a squared plus b squared? Well, obviously you want to complete the square, and this is how you would do it. And this is, you would first prove that, you would prove this part of the inequality by completing the square and using properties of a ring and so forth. Okay, here's some examples of basic logic. So if you're given P and Q, how do you prove Q and P? Well, it's obvious, but it's, from a syntactic point of view, it's something that you have to prove. Well, you just take the right hand and the left hand, Q and P respectively, and you exchange them. So that's the proof of that. And more interesting is this proof of not P. Okay, so you might think not P is the same as P, but if you actually get into the foundations, not P is not always the same as P. There's this issue of what's called a constructive logic and the computational forms of logic, where in particular you use the axiom of the excluded principle. P is either true or not true, and the simple proof of this. But that's not a thing, which there's problems in using that. And so you have to use this contradiction sort of mechanism to prove it here. Okay, and then if you get into this, a thing worth knowing is that there's this correspondence. So I started out talking about correspondences between aspects of theorem proving and things in programming languages, and that goes very deep, that a lot of the proofs, the structure of proofs is something you can map directly onto the structure of programming languages. So if you take, for example, how do you prove that P implies Q? Well, you could prove it logically, but you could also observe that, well, suppose I had a function that took a proof of P and always gave me a corresponding proof of Q. Okay, well, that would in fact be a proof of P implies Q just by thinking about it, and then you can, to justify that intuition. That is a valid intuition. And so there's a sense in which these proofs, they look like mathematical proofs, but they can be executed like programs. You can make programs where you can verify. This was a lot of the original interest in this in computer science, that you can write programs which you can prove do certain things or satisfy certain properties. Okay, so let me briefly go through this proof that there's infinitely many primes. And you know the proof from Euclid. So you look at n factorial plus 1, and it's either prime or it's got a factor. And if it's got a factor, that factor had better be, you can prove easily that it's greater than n. And the proof here is exactly that proof, just written in a slightly funny way, which has many funninesses in it. Okay, it's again, why I'll come back to why is it this way? But this is now, we've defined someplace just as a defining property. What's the least factor of this n factorial plus 1 in the integers? And then we have cases. Well, maybe that least factor is prime. Maybe that least factor is not prime. If it's not prime, I have to check to see, I have to argue that the P doesn't divide all of these factors and so forth. And one can trace through this. It's both something which you can understand by close reading, but not that intuitive. Okay, it's really not, it takes a while to learn to write this kind of code. Okay, this is an example, and there'll be a much bigger example of the mechanisms, the IDE that a computer has to help you do this with this current state of the prover. You put the cursor someplace, and here's exactly what all the variables mean and what you're still trying to prove. Okay, this is a more real piece of mathematics in terms of the theorem about Fourier transforms. And again, there's a lot of pre-proven. These are all basically things already proven in the library, MathLib, this 1.7 million lines I referred to. Okay, and there's quite a bit there, as I said. And what's going to be important shortly is there's a fair amount of probability theory, okay, but there's a certain amount of functional analysis. There's not that much of, again, kind of basic facts about functions to do calculations. It's possible, but it's awkward. This is a long list of things, but compared to what's in a textbook about manifolds, it's really just chapter 1 or chapter 2 maybe. There's a fizzling, beginnings of a project more oriented towards physics, which I'll recommend in this slide. Okay, so anyways, I've been following this for quite a while and have wanted to do a physics project, but again, it's not easy. There's not so much in the library, but what is there now, various things, but in particular probability theory, and this is actually very nice from the point of view of quantum field theory, as was in fact in Christian Ferko's talk. It's a very straightforward reformulation, a correspondence between the standard quantum mechanics and a language of probability theory and stochastic processes that you can formulate a thing that is equivalent to a quantum field theory as a probability measure. And then you want to show that this satisfies axioms that show that you can use to reconstruct the quantum field theory, the Osterwelder-Schroeder axioms. And this is the project that Sarah and I are trying to complete, okay, to prove these axioms, formulate them, prove them for the free field. Okay, so these are axioms that govern the generating function. So d mu is this functional measure, which you can define in many cases, though not the most sophisticated physics ones, but in many cases you can define it mathematically. Then given that, this will be a generating function or correlation functions. And then there's a fairly short list of axioms, which fortunately was on the in previous speaker's talk that we need to formulate. And here's how they look in lean. So this analyticity axiom, we give it a probability measure. We want to look at the generating function. We're going to basically ask that some appropriate weighted sum of test functions with analytic variables is entire in the variable z. So that's a thing you can say. Most of, I mean, this thing we defined, but we didn't have to do very much work because this is basically there is one variable generating function already in the MathLib. We had to soup it up a bit, but not that much. This is the regularity bound from the previous slide, a pretty direct translation. There's a special condition for the two-point function. This is the reflection positivity that was played an important role in Christian's talk. And now we're looking at stars, this reflection operation. We have a function, and the expectation of the function with its reflection should have zero imaginary part and non-negative real part. So all these things are not that hard to say, and in fact in a fairly sensible way in lean. Okay, and so it's I wouldn't have said it even a year ago, but with a huge amount of work, one could formulate interesting quantum field theories. I think the most interesting one, which is it hasn't been done, but kind of within the range of the existing technique, would be the 2-2 supersymmetric gauge linear sigma models, and you can imagine getting rigorous results on mirror symmetry. And so the take that I'm going to now justify for the rest of the talk is to say, this exists. This is very hard actually to use. You would use it if you really, really needed to prove that something was right. But AI is going to bring all this into much closer reach to make it really much easier to use. Not in the distant future, but over the next 1, 2, 3 years. Okay, so I'm going to actually not spend a lot of time on this. You can read these slides later. Now, you can debate as a physicist, we have good arguments. We have convincing arguments for example, mirror symmetry. What do we gain by rigorously proving it? And it's an interesting discussion to have. But what I think would be a very clear win is and a great advantage of being able to take an argument or result and just verify it on the computer, say, yeah, this is correct. I mean, maybe it's not proving the thing you think it is, but the thing is stated as it's stated, you've proven that. And then if you think about, well, using prior work, reproducing prior work, catching up with prior work, a collaboration. I can split my project into 100 parts, but where's the 100 people that I can trust to do the 100 parts correctly? Well, if I can check the answers, then of course that makes a much lower bar. I could even have an AI try to produce the answer if I can check at the end that it's right. And so I think the early version of this, people talk about superintelligence and who knows, but the early version is, assuming that we have the energy to do it, we can hire 1,000, quote, AI graduate students, not even as good as a human graduate student, but able, in some cases, to solve problems, and then we can verify the results. And again, once this technology comes into range, that starts to make much larger projects possible. Another of these questions is, well, do you need formalization for computer proof? Maybe you could work just with the text. Maybe you could work with some other thing. Physicists don't argue rigorously, but they do seem to all agree that, yes, this was a solid argument and you proved your case. This has this particular gap. And it's very interesting to ask, what is the basis of this reasoning if it's not rigorous math? I myself tend to think that it could be made rigorous, that you could state a lot or maybe all of our additional assumptions as axioms and then think of it in this same, much more analogous to mathematical reasoning. I'll say a little bit about this because this is also very important for physics, that there are these other sides of checking computations and getting provable results that apply to numerical and symbolic results. And the short way of saying that is, suppose you have this big calculation, do you want to do it in lean, or suppose you already could do it in Mathematica. Mathematica is very adapted to that. Mathematica ought to feed the proof that this calculation is correct, what you just did, into the theorem prover and have the best of both worlds. And there's ways of getting numerical calculations, phrasing them so that you are proving rigorous results. I've talked about this in other talks. This is an ongoing project to reproduce cases of Yale's theorem using the numerical results to rigorously prove that Calabi-Yau metric exists in certain cases. This is the comment about Mathematica. Very often you can put out an exact statement. The machine could in principle put it out. Here is the thing that was computed. Here were the steps that were followed. Therefore, you have a rigorous proof of your calculation. Okay, so as I said, the real reason to get interested in this now is that this is very rapidly advancing. This started of interest to AI researchers really with AlphaGo. And then there's one style of argument that says that language models, all of the very successful deep learning, is statistical. And so a statistical system, you might think, would have trouble getting results with 100% accuracy or reliability. And well, certainly that is the case at the moment. They make mistakes, they hallucinate, and so forth. And so it could be that you need to couple them to a verifier to really make long arguments. And this is a point of view that many people in the field, but not everybody have. Reinforcement learning was before the language models, this was the main line of AI trying to make proofs. This is the news of last year and the year before, DeepMind's accomplishments and gold medals at the IMO. Of course, most recent news is the July 2025 IMO International Math Olympiad, and there were 4 groups that had systems that got medal-winning performance. OpenAI and Google actually used language models, more or less fine-tuned versions of their standard language models that fine-tune on big sets of these problems, and really they did the reasoning with informal language. And a couple of other companies used systems, much like the alpha proof of last year, that were coupling a language model to the lean theorem prover. So this is, again, it's not at the point where this shows you can do anything for research, but still, this is a very big advance already since last year. And this is really taking off, or at least the beliefs about this. So DARPA has recently started a program called XMath, which the explicit goal is to make formalization and make the computer either auto-formalize, directly translate the paper into this formal language, or by helping the user use it, but to speed it up by a factor of 100. And that would very quickly bring a lot of the problems I talked about within range. Just a month ago, a company out in San Francisco called Morph Labs actually did this for a real research paper. They asked a mathematician, fill out some more details, make what you would call a blueprint. And he filled it out, but not in Lean. He filled it out just in regular math. He made the paper something like 3 times as long, and then their system was able to just read it and translate it into Lean and verify it. Okay, so that's kind of the state of the art. Now, if you've used coding assistants like a Copilot or coupled to language models, you know that these are actually pretty good. They have some ability to write programs on their own. They even as of last year, Lean, I would have said, in the experience of using them, was that there's just not enough. There's 1.7 million lines is very little code compared to what you would need to train a language model. But their general ability seems to be enough to now be very useful assistants. And this has been really very important in our in trying to carry out this project. So I'm about to put on a video of Sarah doing this last axiom of ergodicity, which I left off of the previous list. So this is physically in quantum field theory terms related to uniqueness of the vacuum and also cluster decomposition. So we're going to relate an expectation value under the measure to the integral over time evolution of the operator. So we're equivalently to say there's only one time invariant function in L2 of this measure. So let's see if I can get this thing to work.
As Coder's insider tool in agent mode coupled with the Lean MCP LSP protocol.
Let me start it again. I see it's not. I just want to start from the beginning, and there we go.
In this demo, I will explain the scaffold I have for the OS4 axiom and demonstrate the power of the VS Coder's insider tool in agent mode coupled with the Lean MCP LSP protocol. So what exactly do we want from a formalization? Well, remember, we aren't proving ergodicity. We are merely trying to formally state it. The plan for the scaffold I have is to allow T to move states and preserve the sizes of the ruler mu. It defines invariant sets, ergodicity, and the orbit average of AR of F. It uses the Birkhoff is the time averages convergence theorem, which in the ergodic case looks like A sub RF goes like the integral of F d mu almost everywhere. The scaffold then bundles all of these statements into os4.lean.
This is a file.
Okay, now let me walk you through line by line of the scaffolds that we have. We begin by looking at the imports. These imports are important because they are utilities to talk about mu, integrals, and limits, which we're going to need for the time averages equals space average part of the setup. Next, we fix our dimensions to 4. Our spacetime is r to the 4 with its Euclidean structure, and the measure on spacetime is the volume. We have our namespace, which means that everything in our scaffold lives in OS4. We have our flow structure and definition. So a flow is how the system moves in time without breaking measurability. In physics, think of spacetime translations. So our structure flow omega says that we have a flow on omega, where first T maps time and state to a new state, jointly measurable in time and state. At time 0, T is the identity. We have a composition law, which states that doing T then S equals doing S plus T. This functionally acts as a play button for T, with the algebra that we need before stating any ergodic theorem. Next, we have lemma measurable T, where this fixes time T and has a map omega, which goes to T sub T omega, which is measurable. The proof idea is that it is a slice of the jointly measurable map. So we build S of omega equals T omega, then T little t equals the joint map after S. We have a definition of the orbit. So the orbit of omega is everything you can reach by flowing in time. And this is useful because time averages run along orbits. Next, we formally state our time averages. So we have thus a zero time average. So you watch f along a path from 0 to big R, integrate in S over the closed interval and divide by R. If R equals 0, then you return 0. Below that, lemma measurable time average. As a function of omega, this average is measurable, where the idea is that we have a joint map S omega goes to f of t s omega, which is measurable and integrable over S. Though there is an issue with this, so the proof stub ends in a sorry, and we actually have to fill in the rest of this lemma.
Yeah, just that's where we're getting. So the computer, a language model, did a pretty good job of writing a first draft, and then it gets to a certain point, I don't know how to prove this, sorry. And then we're going to use it to try to improve this.
But this is useful because we need to talk about almost everywhere convergence of our averages. Below that, we have def invariant under, which basically just says that we have no distortion of size for every t of t, preserving mu. Okay, invariant set. So if A is a motion proof, measurable, and membership is the same as almost everywhere after any move, where we have our inverse as the pre-image. We have an ergodic action definition, where ergodic means that there are no non-trivial islands. Every motion-proof set has a measure 0 or full measure. This is just the set-based definition that our scaffold uses. We have several other functions that still have some sorries in them that are useful that we're going to pass off to the Birkhoff theorem. So now, okay, theorem, ergodic if and only if time average converges. Well, Birkhoff is the time average convergence theorem for measure preserving dynamics. In the ergodic case of those time averages converge almost everywhere to the space average, the integral of f. So here we express this as the limit as r goes to infinity, and we replace that filter with at top later for clarity. But we still have a sorry. But this is the target promise. The time average equals space average almost everywhere under ergodicity. So that's a very important statement. Next, we have some helper lemmas. Now, if we scroll a bit further down, we have a concrete flow on R4, where we define a spatial translation, where we translate only the ith coordinate. We're also going to want to check some of those tools. And then at the bottom, you just see that we've bundled all of these together to actually state the OS4 axioms. So we're bundling together assumptions and the Birkhoff conclusion, a probability measure, a measurable flow, preservation, ergodicity, and almost everywhere convergence of time averages. And that's the upshot of what is actually occurring in the scaffold. Now I will show the power of the chat agent and the lean LSP MCP protocol. So I'm going to ask our protocol to fill in one of the sorries. In particular, I'm going to ask it to fill in the sorry at the spatial translate group, where we have the expectation that what this function is trying to do is to create a flow that must satisfy the group law, where we have big T S plus T is equal TS TT. So here, translating one of the coordinates by S plus T should equal the translation by T and then a translation by S. Similarly, I'm also going to ask it to fill in the sorry for the spatial translate identity, which just states the identity law, which should just be that shifting by 0 does nothing. And then I'm also going to ask it to create some checks along the way and see if it can verify the properties of what it just filled in. So let's begin with doing that and see how far we can go.
just going through and writing new code in the green sections and telling us what it's doing.
Now that our agent is finished, let's actually look at what the code does. So in the spatial translate group, it looks like this uses ext_j to prove two functions are equal, and it compares their values at each coordinate j. It unfolds the definition with simp-only spatial translate, and it splits cases where j equals to I or j does not equal to I. And if j equals to I, it shows that xj plus s plus t is equal to xj plus t plus s via adcom and add-associative. And if j doesn't equal to I, then both sides simplify to xj. Okay, this looks okay. So why is it okay? It looks like this reduces to elementary facts about addition, and the case split seems exhaustive, and X makes pointwise equality rigorous. And this is useful because it ties back to the play button composes that we were using, which certifies spatial translate, satisfies the group axiom needed to build a flow. So this is useful for the ergodic theorem we're going to use later. Okay, and let's check spatial translate identity. So what does the code do? So again, we have xj, then we unfold. We have the case where j equals I. This looks like xj plus 0 is equal to xj, so you're just adding by 0. In the case where j doesn't equal to I, both sides are just xj. Okay, this seems okay. This is just trivial algebra in the same case split. And this does confirm the other group axiom for flow. So with group and id, we have the algebraic skeleton for the flow on R4. Okay, and now let's look at the verifications. Okay. So it looks like this is a sanity check that's picking a concrete I equals 0 and t equals 0, a simple point x, and showing the identity law still holds. What is the code doing? So it's just applying spatial translate identity, and it instantiates the general theorem on a toy example. This seems okay. It's a bit redundant. And this does demonstrate the laws aren't vacuous and that they behave as you would intuit on real coordinates. Okay. Let's look at the second verification, which is the same laws above, but proved a different way. So in this one, it uses the fun X directly instead of the X tactic. It unfolds spatial translates. It does the same split at j equals to I and uses add 0 in the j equals to I case. Okay. So fun X is the principle behind X, where the proof is fully explicit and elementary. Okay, again, it looks like this shows the result is robust to proof style. No new math, it's just an alternative definition. Oh, no new math, it's just an alternative derivation. Okay, let's look at the verify spatial translate group concrete. Okay, so it's a concrete check of the group flow law for fixed numbers, I equals 0, s equals 3, t equals 5, and a simple x. So what is the code doing? It's using let bindings and then applying the spatial translate group. This is just a quick executable check where it instantiates the general law. Okay, this just gives us more confidence on how our flow law behaves on real examples. The same is also true for the verify spatial translate group alt proof. So another proof of the group law pointwise. Okay, it looks like this mirrors the first proof, but it just spells out this a bit differently on the calc chain. Okay, great. I think that this also does a good job confirming the group law on the coordinate level, which is exactly what we need to treat translations as a bona fide flow. Okay, so anyways, the sorries that it filled in look pretty decent, and the checks at least make sense. And this is just some of the power that you have at your disposal now with new AI tools for coding up statements in Lean.
Good, very good. Okay, so this technology works, and I described some of the advantages, but they were outweighed in the past by the difficulty using it, but AI is rapidly solving that, and I predict that this is going to continue to improve over the next year, 2 years, 3 years, to the point where, I don't know if we'll be programming in Lean or some more human-readable thing, but we will be using this with the same level of ease that we might use Mathematica or Sage or one of these symbolic calculators. And of course, there's many, many examples like that we could talk about in AI. And I think the lesson is that we should all really become much more ambitious because we're going to get these much better tools. We should be preparing to work on harder problems that we will be able to grapple with. So I'll stop there.
Questions for Mike?
All right. Arthur.
I know a little about quantum field theory, but I didn't understand what you have proved about the ergodicity in OS4.
Okay, well, there's a bunch of statements that, basically the ones we were focusing on was that time translation is a semigroup. And,
but in 4 dimensions, probably any probability measure satisfying OS1 through 3 is ergodic because they're only linear fields.
Well, our arguments were assuming 4, but that's just a parameter. The same, we could easily change
dimension
that.
2, it's known there are examples which are ergodic and non-ergodic, and how do you distinguish them?
Oh, yeah, well, that's right. So at this point, we are just formulating the axioms and all the structure that means that they make sense. So, in your book, you can describe that axiom in half a page, but we need to prove that the objects we're talking about have the properties that, as a mathematician, you could just cite, because they're in textbooks. And so that's mostly what we were doing here. We were not doing anything deep at all. We were just saying, yes, time translation is a group of the sort that acts as a group action, the sort that you would expect. There were quite a bit else there to show that, indeed, the action makes sense and a strategy for proving that you have ergodicity, which was just a strategy. Obviously, there's no general proof of ergodicity. And I think the current project the ambition I think that we can get is to prove this for the free field, so in the linear. And so in that case, it's we can do explicit calculations. But I think again, it's not like this is very easy. The size that it filled in were things that basically had to do with compositionality of properties like measure preserving and so forth. And once you start to get the things where it's not really obvious or your definitions are improper, it tries, occasionally does the right thing, but it needs a lot of help. It's really an assistant at this point, as opposed to So it's going to take us, I don't know, maybe a couple more months to finish this. But again, the technology is advancing much more quickly than anybody thought, and it's hard to predict exactly the time scale. But this time scale that says that within 2 or 3 years, the thing might just be reading your book and putting out this stuff is entirely possible, and at the very least something which, as I cited, the solicitation of the DARPA grant proposal, we will make it 100 times faster as the goal of our research. If it would have taken you a year, maybe it will take you 3 days with this technology.
Okay, for things like Fermat's last theorem, the roadmap also is quite important. The roadmap, or building a roadmap for theorem proving. So it's very interesting to see the things for ADS-CFT or whatever physics statements we are. How close are we to having roadmaps for these physics problems, and what are the challenges for these?
Well, again, we were very advantaged by being able to use Arthur, Glim and Jaffe, which this is a subject which has already been turned into mathematics, and so the roadmap, again, the first step was to take not that book, but our paraphrases with some supplementary material of describing how do you, what are the axioms, how do you prove the axioms, and giving that to, I believe Gemini, I forget which one Sarah used, but, and getting this initial draft And then the roadmap would be to go back to our draft and say, it didn't do a very good job here, let's spell this out more. And that's an iterative process, and that's very practical here. Now, you could ask for a physics problem which is not clearly statable in terms of rigorous mathematics. And I think that's the very interesting question that we should be all starting to ask ourselves, which is that you might defend the position that formalization by definition requires rigorous argument. And I think that would be a very strong position. But then it's actually a jump from that to say, well, rigorous argument must be rigorous argument of the sort that the mathematicians do based on their foundations. Maybe there are other ways to do rigorous arguments. Or maybe there are, again, a lot of calculations are rigorous, basically. A lot of what we do is rigorous. So maybe by supplementing it in another way, we can also use this technology.
Other questions for Mike, as I almost trip. I have a question. Oh, yeah, Jacob. Then I'll ask. Yep.
My question is about the word sorry. So yesterday during the panel discussion, there was some discussion about how LLMs now they have difficulty in telling when they can't tell the answer or saying sorry.
Right.
So are there any tricks here? Is saying sorry a good thing? Is that something we can provoke?
Well, for sure it's a good thing. That's right. Now you can ask, that's right, more broadly. Indeed, language models have this problem. We'd much rather, they often say, I don't know, than make something up. And so I have thoughts about that. I mean, but my basic thought would be to say that, although who can say, because this is, the training methods are kept secret, but I would say that training on tasks and data sets where you encourage that, where the part of the task is to decide whether the thing knows and to reply properly in either case would be certainly valuable. Now, how far that takes you is not clear, but at the very least you should do that.
Other questions for Mike? Yes, Fabian.
So assuming you had an army of postdocs or LLM agents or whatever, and you had formalized let's say the Harvard graduate curriculum in physics,
right.
What would you ask the machine? Or what would you try to prove or formalize or check?
Me personally?
Yes, you personally.
Well, I mean, I was talking with Arthur this morning about the Yang-Mills Millennium Prize problem. That would be certainly an attractive goal. I mean, it's kind of beyond where we're at, but certainly one could work on ideas. I mean, there's a huge amount of physics one can do. The most concrete thing I think I mentioned here is that I think the project of constructing the two-dimensional gauge linear sigma model would be, although a lot of work, at least it would be close to what, based on the ideas that the mathematicians have already developed, and then you could hope to show that it's conformal and do like the Dixon, green Flusser argument for mirror symmetry. That would be an example. I mean, again, in terms of physics of, not trying to solve a math problem, but how do we use this to help us make contact with the real world? I mean, an obvious, what I said in string phenomenology is more or less, if we have to go through thousands and thousands of string vacuum and check them all, then we need these thousands and thousands of AI assistants to do it.
I mean, this might then be going back to the question about roadmaps, but is it clear that the Millennium problem is decidable?
Which problem?
The Yang-Mills problem, for example.
Yeah, I think that's clear. Arthur, you must have gotten that question in the past. Is the Yang-Mills problem not clearly decidable in the mathematical sense?
Do you want to answer that question?
I think that in a finite volume, it should be possible to prove the existence of Yang-Mills in 4 dimensions. About the infrared problem, I'm not sure.
Okay, I mean, because there are, the thrust of the question is that there were subsequent results that you can construct quantum Hamiltonians for which the existence of a gap is undecidable. So it at least opens the possibility that the mass gap is undecidable. Now, I don't know a paper that proves it's decidable, but I could give you arguments that would make me pretty sure.
Okay, let's do that afterwards. Thank you.
Other questions for Mike? I sort of have a very fast one. Sorry, Marisa. Marisa's giving me the you should be done look. Mike, you've been telling us for years that theorem proving is awesome, and one of the takeaways I've gotten is lean is hard. Apparently, lean's not that hard for Claude Sonnet 4. We just learned. I'm curious when you saw this working with Sarah, how much it shocked you, because if I use agentic mode on Copilot myself regularly, usually to do very simple things like have it implement some algorithm that's in every computer science textbook. I think the thing that really surprises me, and I'm inviting you to comment on, is that the amount of lean training corpus out there is a lot less than the amount of Python.
That's right.
And there's an enormous number of quantum field theory textbooks, but not that many of them know about OS4. And so it seems to me, I invite you to comment on the reasoning that's happening and the size of the corpus and so forth, because I found it really impressive what happened.
Yeah, no, I quite agree with you. Shocked is too strong a word, but surprised, yes. Because last year the models certainly could not have done this.
Very good. All right. Well, with that, Mike, thank you very much.